Now in the rest of this lecture, I want to discuss two different applications of Markov chains. The first is an example of ranking objects. And so this example is going to show how we can use the stationary distribution of a Markov chain that we construct on our data to rank objects. The specific data that we're going to consider for this type of a model consists of pairwise comparisons. So imagine we have S objects or S teams or S athletes that are competing against each other. Or we could have S objects being compared where users are selecting their preference between two different objects. Our goal now is to rank the objects or rank the teams or the players from best to worst using a Markov chain. So that means that we need to somehow find where a Markov chain can be applied to this problem. The way we're going to do this is by constructing a random walk on all of the objects. So let's focus only on teams for now. If we want to rank sports teams, then every team is going to be one state in the Markov chain. So if there are 1,000 teams that exist, there are going to be 1,000 different states, and so our Markov transition matrix M will be 1,000 by 1,000. We want to construct this transition matrix so that the stationary distribution of that matrix first exists, and secondly can be interpreted as telling us who the best teams are and who the worst teams are, and also give us a degree of everywhere in between. So notice, without telling you yet what the model actually is and how we construct this, that we aren't going to actually have a sequential model of the actual events. So that's the thing to pay attention to, that even though we've motivated Markov chains as being a sequential model, the way that we're going to construct this matrix does not take time into consideration, that we're actually using the Markov property as an artificial modeling construct where we can now interpret the stationary distribution of a Markov chain as giving us something meaningful that doesn't, but the Markov chain that we're constructing doesn't actually correspond to anything meaningful in reality. So this is where an abstract sort of model is very useful, where we don't enforce that it has to actually correspond to something happening in reality. Okay, so we want to construct a Markov chain between these objects. Again, we're just going to focus on ranking teams because it's intuitively very easy. So we want each team now to be a state, and we want to construct a probability of transitioning from every team to every other team. And the way we want to construct these probabilities is that we want to encourage teams to transition from the losing teams to the winning teams. So we want to move to teams that win we want to have a higher probability of moving to teams that win and a lower probability to move for moving to teams that lose. For example, one way that we can do this problem is we can construct a transition matrix where we can only transition between teams if we have a game played between those two teams. So if two teams don't play each other, then we have no information about how they relate to each other directly, and so we aren't going to have any probability of making a transition from a team to another team. So for example, if team A beats team B, then we're going to create a link between state A and state B, or team A and team B, where we now have the potential for transitioning between those two teams in either direction. Except now we want to make a probability of transitioning from one team to another, and we want the probability of transitioning from B to A to be high if team A beats team B. So if A beats team B, then the probability of transitioning from B to A should be high, relatively speaking, and the probability of transitioning from team A back to team B should be low. So it's not a symmetric probability. We have more probability of going from B to A than we do from A to B if team A has beaten team B. And there are many ways we can create rules about this probabilities. One thing we can do is take into consideration the score of the game. So if it's a close game, that will make it a weaker skewing. Whereas if one team beats another team by quite a bit, then the transition will be very biased. Going from B to A will be much higher than going from A to B. So these are arbitrary modeling choices that can be made. So before I show you the results of doing something like this on real data, I want to give my own arbitrary choice of how to score these things. So this is what I've chosen to do. What we do is we initialize a matrix M hat to be a matrix of all zeros. So if there are 1,000 teams, then it's 1,000 by 1,000 matrix of all zeros. Then we iterate through every game one time to construct the transition matrix as follows. If we have a particular game between team J1, so this is the index of team A, J1, and the index of team B, say, is J2. So imagine we have a game between team with index J1 and team with index J2. Then we update the transitions in this way. So we want to update the probability of transitioning from team J1 back to team J1. So this is a self-transition. If I'm in state J1 now, then I can still at the next time point stay in state J1. So you notice in all of these Markov matrices that we've been discussing, we have not assumed that the diagonal is equal to 0, that the diagonal can also have some probability. In that case, we have a self-transition. So we say that team J1 can now update the weight of transitioning to itself by taking the old weight, adding to it an indicator that it won the game. So this is either 0 or 1, depending on whether that team won the game. Plus, for example, we can add the fraction of the total points that it had. So this, if it's a close game, this will be close to 0.5. If it's a blowout, this will be close to 1. It's a fraction of all the points scored in the game that were scored by team J1. So we update the self-transition by taking the old value and adding to it these points. Similarly, we update the transition between team J2 to itself by taking the old value and adding to it an indicator that team J2 won. So either one of these two events will be true and the other will be false, plus team J2's fraction of the total points. So these are updating the weights of the self-transitions. Now, to update the weights of transitioning from team J1 to team J2, we take the old value. So if they've already played each other, then this will be non-zero. If they haven't, then this will be 0. We add to it an indicator that team B wins. So if team B corresponds to J2, then we want to increase the weight of transitioning from J1 to J2 by adding a point, a 1 to that transition, plus the fraction of points that team J2 scored. And then transitioning from team J2 to J1 takes the old value, adds to it an indicator that team J1, team A, with index J1 won, which now increases the weights of transitioning from J1 to J2 because J1 beat J2, plus the fraction of points. So we just manually do this. I've made up these points, but it's a meaningful Markov chain where now we tally up all of these points. We then construct M by normalizing every row so that it sums to 1. And now we can intuitively imagine that there's more flow towards the good teams. If I imagine in my head walking from team to team, what's going to happen is the teams that win a lot and win by a lot are going to be transitioned to with higher probability and are going to stay to them. So it's easy to think for a while about why this could work. For example, if a team wins a lot of games but plays against very bad opponents, then if we transition to those opponents, with high probability we'll go to that team that wins a lot of games. But if a particular team has only beaten very bad opponents, then we're never probably going to make it in our random walk to those bad opponents in order to get to that good team. So this is where some of the intuitions have to come in to see why it's not enough to simply win a lot of games. You have to also win a lot of games against other teams that win a lot of games. In that case, you're going to transition to those other teams more frequently, which means because you beat those other teams, they'll transition to you more frequently. So the stationary distribution can encode the probability of which team I'm going to be at an infinite distance from now, and we can interpret the highest probability team, or the highest probability state, as corresponding to the best one, the second highest probability team corresponding to the second team, and so on. So to give you an example of this on real data, what we have here are all of the college basketball games from the 2014 to 2015 season. So in total, there were 1,549 teams. So I'm assuming that this is taking into consideration all divisions of basketball. So there are this many different college basketball teams that are in the data set. In total, there were 22,033 different games that were played between two teams throughout the entire season. So this is the scale of college basketball. I created a Markov chain exactly like on the previous slide, constructed this stationary, I found the stationary distribution by finding the first eigenvector of the transpose of that chain and normalizing, and then ranking the teams based on the probability in that stationary vector. So that's what's shown here. These are the 25 most probable teams. This score is the probability of being at that team an infinite number of steps from now. So you see that even though even though this is the best team, the probability is still extremely low. So the probability of being at the team Villanova is very small, but still more than every other team. And then here on the left, what is shown is the USA Today coaches poll. So many coaches were asked to give their belief of what were the top 25 teams. And these are the experts this is expert opinion. And all of their polls are taken, combined, and a final top 25 ranking is given based on their collective rankings. And so you can see that the Markov chain, very quick Markov chain without using much expertise, with using zero expertise about what basketball even means. There's no meaning to what the Markov chain is doing. It has no interpretation whatsoever about what exactly it's finding the stationary distribution of. It's still able to give a top 25 ranking that compares very favorably with the opinions of 30 experts who do this full time. So Villanova, North Carolina. You can pause the video and see that Markov chain is the Markov chain in this case is able to learn a top 25 ranking purely on the results of the data of the results given by the games. So this is the data set, takes it and is able to compare favorably with the experts.